In the last video, we saw how to find a derivative using the four-step process. In this video, we're going to focus more on common problems and common uses for the derivative that we found in the last video. So we are going to be working with the same function from the last video, g of x equals x squared minus 2x plus 1, which also means we'll be using the same derivative, g prime of x equals 2x minus 2. So part B asks us to write the equation of the tangent line to g of x at x equals 3. If I want to write the equation of a line, let's just forget about the word tangent for a moment. If I want to write the equation of a line, I need a point and I need a slope. For the point, I need an x value. Well, this x value was given to us, and that will almost always be the case. You'll almost always be provided with that x value. So in this case, it's x equals 3. We do need a y value, though, to find the other half of this ordered pair. And then I'll have my point. The other thing I need is a slope. And if I have a point and a slope, I can write the equation of a line. So I need to find a y value and a slope. Doesn't matter what order that you find those in, it's really up to you. I'm going to start with the y value first, though. So in order to find the y value of our function at x equals 3, I'm going to look to the original function g of x. And I'm going to take the x value that was given to me, x equals 3, plug it in, and evaluate my function. So for my y value, I'm looking at g of 3, which is equal to 3 squared minus 2 times 3 plus 1. So this is equal to 9 minus 6 plus 1. So let's see, 3 plus 1, I've got 4. So I end up with a y value of 4. So there is my y value. The only thing I need now is my slope. Well, we want to find, in particular, the equation of the tangent line. And if I want the slope of the tangent line, well, we said that was one of the big interpretations of the derivative. It's one of the reasons why we care so much about the derivative. So if I want to find the slope of the tangent line at x equals 3, I'm going to take the same x value, x equals 3, and this time I'll be plugging it into my derivative, g prime of x. So to find our slope, we'll look at g prime of 3. So here that's 2 times 3 minus 2. 2 times x equals 3 minus 2. So 2 times 3 is 6 minus 2. Here I end up with a slope of 4. So this is, I think, one thing that we will have to keep in mind, and it can be tricky to remember at first, is we have a y value which is given to us by the original function, and the slope which is given to us by the derivative. These two things can be easy to mix up, but it's really important that we keep them straight because we will be using them both. So if I'm looking for a y value, I want to look at the original function. If I'm looking for a slope, I want to use the derivative. At this point, I've got everything I need in order to write the equation of my line. I've got my x value, my y value, my slope. You can write the equation of the line using either slope-intercept form, so you can use y equals mx plus b if you like, or you can use point-slope form. You can use y minus y1 equals m times the quantity x minus x1. And that's my personal preference. That's how I'm going to be finding the equation of the tangent line here. So I'm going to take my y value, plug that in for y1. I'm going to take my slope, we'll plug that in for m, and then I'll take my x value and plug that in for x1. So y minus my y value is 4 equals m, our slope was also 4, times x minus my x coordinate was 3 here. And I'm just going to take this equation and solve it for y. So y minus 4 we can distribute over there on the right-hand side. 4x minus 12, and then add 4, so I end up with y equals 4x minus 8 is the equation of our tangent line. So if we were to sketch the graph of our function g of x equals x squared minus 2x plus 1, along with the equation of the line y equals 4x minus 8, we'd see that we have that line being tangent to our graph at the point x equals 3. I'm going to go ahead and post a picture of that below this video, so be sure to check that out so that you can see that we did in fact actually find the equation of the tangent line. Part C asks for something different. It says find the x values where our function g of x has a horizontal tangent line. So this time we're looking at a horizontal tangent line, and I first of all just need to think about, well, what does a horizontal line look like first of all? Let's think about that for a moment. A horizontal line, if I were to sketch a horizontal line, I could find the slope of that horizontal line. I know the slope of a horizontal line is 0. I'm going to need to know that piece of information. The other thing that stands out to me in this problem is I'm thinking about tangent lines. And when I'm thinking about tangent lines, I'm thinking about the derivative. So really, almost every time you see that word tangent line, I want you to start thinking about the derivative g prime of x, which we said was 2x minus 2. So I want to find the places where our function g of x has a horizontal tangent line. Well, we know that the derivative g prime of x tells us the slope of the tangent line. So g prime of x is equal to the slope of the tangent line, but we don't want just any old slope. We want specifically a slope of 0. So let me underline that. I want a slope of 0 here. So I want in particular a slope of 0, so I'm going to take my derivative g prime of x and set that equal to 0. So I'll take 2x minus 2, set this equal to 0, and I'm going to solve this equation for x. So I can add 2 to end up with 2x equals 2, so I end up with an x value of x equals 1. That's where I have a horizontal tangent line. And I'll go ahead and post the graph of this horizontal tangent line along with our function as well, but I can sketch this one in really quickly. If I were to graph our function should look something like this. And as I sketch in x equals 1, or if I kind of notice what's going on there at x equals 1, if I look at the tangent line there, well, the tangent line should be horizontal, which is exactly what we found here in part C. I want you to just keep in the back of your mind, I want you to be thinking about what else is special about this point. What else is special about our graph of our parabola here in this case at x equals 1? Because there is something pretty important about our graph at x equals 1 that you might argue that that's the most important part of this graph.